Okay, welcome back to our wonderful Rust Embedded class with Professor Brad. Today we dive more into the embedded board, trying to demystify and understand the embedded board and also doing more of coding and see how things have been done. Thank you very much. I'll giving the mic to Professor Brad to these things. Welcome back, guys.
Thanks, everybody. Good to see you. I'm excited to keep going with what we were doing from previous days. I was just talking with Mordecai, and I think what we're going to do is we're going to have 2 classes next week, and then finish up the normal instruction. And the Monday after that, we'll have one more meeting, which will be just sort of a debrief and a chance to answer questions and that kind of thing. So that's the plan for the rest of the session here. Let's start by, one moment, please, looking at the course outline and seeing where we are. So last class, we poked at blinkies for the most part, and then we, at the end, did this LED roulette thing to sort of see how to use the BSP. From here on out, we'll be pretty much using the board support package as our main tool. So the next lecture here is going to be, I don't know why these got split into 2 categories, but this today will cover simple input. We'll look at buttons and how we actually input stuff from GPIO pins, and we'll start to look at serial I/O protocols. Serial is one of these annoying and weird topics of embedded that is absolutely essential to what's going on, so we're kind of stuck with it. And we'll look at some applications of that. We'll play around with async serial a little bit, and we'll talk about that, and then we'll talk about I2C and reading the I2C accelerometer. So yeah, that's the plan for today. And so, like I say, let's start with just some buttons here. Let's go look at what am I doing here? And again, this is all from the Microbit 2 Discovery book. The URL is in your course materials. We're not doing anything clever here today. We're just going to follow what's going on there. And the idea here is that if you look at our microbit, you've got these A and B buttons on the side. They're labeled A and B. And the way you read those is exactly the way you think you read them. You have use a GPIO pin, just like you would think you did. But that GPIO pin is now going to be configured as an input pin, and we'll talk about that real quick. So let's start by looking at some examples here. And the easiest way to start probably is this. So here's an example that uses, if you'll remember, a long time ago, we found out how to print stuff to the console. We'll talk a little bit more about that today. But what we're going to do is we're going to use our normal entry point. We're going to use the input pin trait from the digital HAL traits. That just lets us, embedded HAL traits, that just lets us do this ISLO. And the microbit board support package, the usual panic. This is a panic that prints the panic message out on the console, but we're not going to get any panics, so it won't matter. And then this normal stuff so we can print stuff. So what we're going to do here is just print a message when the button's pressed, and otherwise print a message when the button's not pressed. So how do we do that? We initialize printing, we grab the board struct, we get the button A peripheral out of the board struct, and then we just check if it is pressed. Notice that it's pressed when the button's wire is low. And to see why that is true, let me quickly grab our schematic here. One second. There we go. And if we look at our schematic, we'll find the buttons here.
Hello, we can only see the board. Is that what you're trying to show now?
The screen. Dang it! I've done it again. Oh well. So yeah, here's the code I was talking about. Let me walk through it again. There's the entry point, the digital HAL trait for input pin, the board support package, a thing that panics. We're now going to set up for printing. And so we init for printing, we grab our board support structure, get the button A peripheral out of it, and then we just check to see if button A is low. And so the interesting question is why? Why does button A need to be low for the thing to work? And the answer is that this button circuit is wired in a way that's kind of standard, but is also weird. So this is just power. This is just voltage. And the way a button or a switch works like this is what's called a momentary contact switch, is that basically when you push the button down, a wire is connected between these 2 points. And so when you've let go, no current can flow through this. When you push the button down, current will flow through this. And that's all there is to a button. But you'll notice these are wired a weird way. They're wired in such a way that when you let go, there's a path from the voltage to go out this button A port. And so the voltage will be high. When you push down, the path to voltage goes down through this ground here. And for the voltage goes down through this ground here. And so button A will be low. So this is what we call an inverted input. We've got it low when it's pushed and high when it's not pushed. And all this resistor does is keep huge current from flowing through this. It's wired this way so that when the button's released, no current flows, basically. And so it's a lower power configuration, but it's annoying because it ends up flipped. Usually when the hardware people and the software people have conflicting engineering constraints, the hardware people win because software is easier to fix than hardware. So that's why. So every time this button is low, it's pressed. And if I run this example, it should, and I guess I can flip this to the view that lets you see this run. Oh, nice. All right. Well, let's fix that. Turn on the board. That's always a good idea, which now starts blinking. Remember how yesterday we left it blinking? Yeah, that's the joy of Flash right there. Let's try again. And it says, oh, the button's not pressed. The button's not pressed. And if I push down the button, then it says it's pressed. And because it's just in a continuous spin loop like this, it just is printing as fast as it can. If we stop this, we'll see that it's printing many times a millisecond the button message. And the fact that that works at all is kind of surprising for reasons we'll talk about later. But that's it. That's all we need to do to read the button state. Now, the obvious thing to do with this first is to have it only print a message when, what was the name of this? Have it only print a message when the button changes. So let's do it this way. So this is what's called a Boolean variable. It can be either true or false, right? The type here would be bool if we put an explicit type. And that's useful. And we're going to go ahead and say, so now we'll just set this up so that it doesn't print this unless it's changed, right? We only really want to see this when it changes, and that'll make things a lot clearer about what's going on. And so let's try the example modified this way. And now it's not printing anything. And when I push the button, it says button A pressed, button A not pressed. So yay, buttons. And so this can be really super useful. The other thing we might like to fix is that we're spinning here, right? We're reading the button as fast, literally as fast as we can, which is pretty darn fast. But that's okay for now. But if you're doing power stuff, you might want to wait a while after you check, go to sleep for a while after you check by calling a delay to be able to not do that. So yeah, that's it. Buttons, they're not that complicated. Let's go ahead and look at some more examples of all this. The next example is interesting, which is that it blinks while the button is held. And again, it's pretty much all this same input stuff, except now we're going to do both inputs and outputs. We're going to have the button and also the LED. And this is interesting because we've done some really fancy stuff with types. This is Rusty enumerated type, which you may remember can carry data. So here, this is the time that it's supposed to be lit, and this is the time that it's supposed to be unlit. And you'll notice that we want to have 25 on ticks and 75 off ticks here. We've done this fancy thing mostly just to illustrate the enums. And so here, when we go to flip the thing, if it was lit before, we set it to be unlit with an off tick, with off ticks number of ticks to do, and vice versa. And when we're counting down, then whichever of lit or unlit we're in currently, we subtract a tick from that. And we always make sure that we don't ever let that go negative. So here's another type we're using. This says either it's supposed to be off or it's supposed to be blinking, in which case it uses one of these light structs to indicate the blinking state. So all this has gotten very fancy, but the net effect of all that fanciness is that we can keep track of what's going on with all these types, so-called type states, and it makes it really easy to get the code right. It makes you really confident that when you've got it to compile, it will work. And so again, we're just going to set up the LED so that we can turn it on and off, and we're going to get the button so that we can read the button to find out what we're supposed to be doing. And we start with it off. And if we see that the button is pressed, here's the match statement being used with tuples in kind of a fancy way. Button pressed here could be false. It could be true with the indicator off, or it could be true with the indicator blinking. And depending on which of those three states we're in, if it's false, then we make sure that we turn off the LED and we set the state to off. If it's true, that means we're supposed to be blinking. So if the indicator's off, then we set it to blinking. So this is how the blinking starts, and we turn the LED on. And if it's set to blinking, then we count down if we need to, and otherwise we flip it. And so this is where the, if we're out of time, then we flip it to the other state, and also flip this, the LED itself, and then the same thing here. And notice that in this spin loop at the top, the loop that controls everything, we end by just delaying for 10 milliseconds, 0.01 seconds. And we delay for 0.01 seconds just because we don't want to sit here and spin at the highest possible rate. It would be counterproductive, but also because we want this tick time to be predictable, right? So this time of 25 ticks for on and 75 ticks for on, well, each tick is 10 milliseconds. So this is 250 milliseconds, a quarter second, and this is 750 milliseconds, 3/4 second. So now we have nice predictable time behavior. And if we run this example, back to here, if we run this example, then again, we got nothing. And when I push the button here, we see it blink for a quarter second and then off for that. When I let go of the button, again, we see nothing. Then when I start again, it starts again. And notice that no matter where I left it, it always starts in the on state right when I push the button. And that's sort of deliberate. That's how we wanted it to run. So now we're playing with both inputs and outputs. Yay, the button and the LED. And that's fantastic. But let's see what the actual challenge program was that this chapter asks you to run. I don't think the other example here. What does this other example do? I see. This is just a simpler example. It doesn't matter. So the actual challenge of this chapter in the embedded book is to actually make it act like a turn signal, which is to, when you push the A button, blink a left arrow, and when the right button, blink a right arrow. So this is just a combination of all the stuff that we've done up to this point. We set up a pattern that's a left arrow pattern where we have ones where the LED is supposed to be lit and zeros where it's supposed to be not lit. And that looks kind of like a left arrow. Here's the other pattern that looks like a right arrow. Here's one that says we're just in the center. Neither button is pushed. And now what we're going to do is we're going to just do this very simple thing where if I guess we're not even blinking this. I thought we blinked this, but we don't. We are going to show a left arrow if it's blinking left, if the left button's pushed, a right arrow if the right button's pushed. So here we just use the display pins and do that. And then the center LED if neither button is pushed. Notice there's what's called a race condition here. It's possible that, between the time I read button A and the time that I get here, button A is pushed. But since we're looping arbitrarily fast, that just means we'll be a few microseconds late turning on the arrow. I don't think anyone cares, or turning it off. And I don't think anyone really cares. So yeah, let's just run this and prove that it does what I said it does. And here's that running, and you'll notice the center LED is lit. And if I push the right arrow, the right button, it turns into a right arrow. And if I push the left button, it turns into a left arrow, and everybody's excited. Really, the challenge here, I'm going to probably have to rewrite part of this chapter. I didn't realize we left it like this. Should be to have those arrows blink, because that's what a real turn signal does. But here we are. All right. That's buttons as input, and sort of a review of some of the other stuff we've talked about. So hopefully that's all clear. Are there any questions about any of that? No. Okay. Don't be shy about asking questions and comments. The few of you who are in there, I can't tell how many are in there. Absolutely happy to get questions at any time. No, that's not where we are going today. Serial communication. All right. Whoops. All right. So this chapter is just 8. So chapter 9 was about machine registers and device registers, and we're not going to poke at that this trip, I think. Chapter 10 starts about serial communication, and it's basically just a guide of how to set up serial for your platform. If you're on Unix or a Mac, it works one way. If you're on Windows, it works another way. And so I am on a Unix box, I'm on a Linux box, and so I'm going to use the Linux version of this. I would encourage you to read this stuff on your own time from the discovery book to see how that setup works. Yeah. So far, we've seen how to use some simple stuff, the buttons and the LEDs. That's great. But a lot of times you want your board to talk to stuff that's not on the board. You'd like your microcontroller to be able to send messages to the other thing. We've seen how to do some printlns so that we can at least see what's going on. But sometimes you want more than that. You want to connect to the board to something. And the normal way you do that is through a serial port. That's a really common way to do that. So if you look at this board, down here along the bottom edge are all these copper pads. Those are actually wires that go all the way into the microcontroller, and can be driven in various ways. The big ones are not particularly special. They're just more convenient to clip onto. But you can get an edge card connector. Let me go grab one here. This little black thing is an edge card connector, and I can actually plug the board right into it. Let me do that for a second, but let me turn it off first, because always power off things before you plug power onto them. And now, let's see, I think I can show it like this probably. Now, if you look at this, you can see that, no, still not high enough. We'll go higher. You can see that what I've done, I've plugged this board right into this edge card connector. And yes, it matters which direction the board faces. If you turn it around, it won't work. But with this plugged in, I now have access to all these pins as little wires that come out down here, and I can actually mess with stuff. So those edge pins are important for when you want to connect stuff off the board onto the board. Let me put this all back the way it was. This particular circuit, right, is part of a project for my Rust embedded class I teach at Portland State. So the mechanical part of it, the electrical part of it, is pretty straightforward. When you want to when you want to hook an external device up, you get an edge connector or otherwise hook these external wires onto the other device that you want to talk to, and now they're hooked together and you can do stuff. That's the easy part. Why is the autofocus not? I don't know, but it's sure not. There it goes. Looks a little better. So electrically, it all makes sense. And let's look at our schematic again. One of the things we'll see on the schematic somewhere, there's also a diagram somewhere, but I think this is as good as anything. Look at the expansion connector here, shows what pins each of these connectors, each of these edge connector wires is connected to. And the ones we're going to be most interested in right this second, here's ground, here's power, in case you need that for stuff. This we will talk about soon. This we will never talk about, but it's a thing. Some GPIOs. These pins named ring are connected to GPIOs. But the interesting part here is that
Professor Brad.
Oh, I'm sorry, you can't see me again. Yeah, thank you. Let's try that one more time. Thank you for interrupting. I appreciate it. Yeah, you're right. So let's fix that again. Let's see, how do I scroll this over? So what I was saying is there's ground, here's some voltage, here's I squared C, which is a thing we'll talk about in a bit. Here's SPI, which we won't talk about at all. This is just a GPIO. So you can see for each of these little copper connectors on the board what it's connected to. What we're interested in today is actually, if we look on the microcontroller, not the interface one, but the real one, we should see somewhere the UART pins. Where are they? They're super secret hidden UART pins. Why are they super secret hidden? That's super weird. Oh, there we go. UART int TX, and there should be a UART int RX here. That's transmit and receive for the UART. What the heck's a UART? A UART is a universal asynchronous receiver transmitter. That's a mouthful and probably pretty meaningless. What that is what's called a serial port. And so to understand what a serial port is, I'm going to draw some diagrams here. Let me get this out of the way for a minute. Yoink. And get myself a space to write on. Here we go. We'll see what the autofocus does. So a UART is a universal asynchronous receiver transmitter, sends bits out the wire one at a time at an adjustable rate, and the other end receives bits from the wire one at a time at an adjustable rate. So if you think about low being 0 volts and high being 3.3 volts, this wire will go along just being high as long as there's nothing to send. Is that right? I can't remember whether it starts in the high state or the low state. But anyway, yeah, that's right. And then when it's ready to send something, the microcontroller will first drop it low for 1 bit time to send a so-called start bit saying, hey, some data is coming. And then over the next 8 bit times or so, let's see, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, I didn't space that right. But anyway, the wire will be either high if it's supposed to be a 1 bit or low if it's supposed to be a 0 bit or maybe the other way around. I can never remember. Anyway, so the point is that we just send 1 bit at a time of an 8-bit byte out the wire. And when we're done, we also delay for a little bit, another bit time, the stop bit time, set high, and then we're ready to send another byte if we want to. So we just send a byte down the wire as a series of high and low pulses. This bit time is called the baud rate because reasons. Our serial port is capable of, on the microbit, is capable of going very, very fast. You can send at a notional rate of almost 1 million bits per second. So it's a very fast serial port. In olden times, a serial port that could send at 20,000 bits per second was considered pretty fast, but modern stuff is nuts. And so if you were to look with an oscilloscope at the output of this UART as it's transmitting, it'd be this pin right here, 1.08, port 1, pin 8. If you look at the output of this UART as it's transmitting, you'll just see a series of high and lows corresponding to bits of the byte. Hopefully, oh, sorry, you're not seeing the schematic. Back here. If you look here, you just see a series of highs and lows corresponding to the bits of the byte. And that's all there is to it. That's the whole story. So this is a way to send data on a single wire very fast. And usually you want to be able to go both ways. So you have a send wire that can send stuff to the other end. And you also have a receive wire hooked up that can receive stuff from the other end. And it works exactly the same way. So what universal, don't ask, asynchronous, meaning there's no clock governing all this. You can start a byte anytime, start sending or receiving a byte anytime. Receiver transmitter, kind of obvious. It's got both a receive part and a transmit part. And the point is, inside this microcontroller is a bunch of hardware that will reassemble the bits coming in on the serial port into a byte and let the microcontroller know it's there. And on this end, there's a bunch of hardware that will take a byte, break it up into bits, and send it out the serial port. And that's what the UART does. That's a peripheral inside the microcontroller. It's a very fancy peripheral with a lot of modes and options and configuration, most of which we'll ignore. But at its heart, it's a fairly simple peripheral. It is a way to send stuff out of serial port. Now, the twist. Sorry, there's always one more twist. Why is this called UART int TX? Because these pins, this transmit pin and this receive pin, are not actually connected to your edge connector. Yeah. Instead, what they're connected to is our interface microcontroller up here. You'll see UART int TX goes into here, and UART int RX goes here. And so it turns out that we're already using that serial port, and we're using it to talk from the microbits computer to the interface computer that's actually connected to the pins. So why would they do that? Why would they do it this way? Well, mainly because in the old days, your computer might have a serial connector on the back. So the point is, the thing you normally want to connect your microbit to isn't some wacky device. Normally you want to connect your microbit to your computer via this serial port. But computers don't have a connector on the back with a transmit and receive on them for serial data anymore. They used to. When I was a boy, PCs had them for a long, long time. But anymore, that's not a thing. That's all been replaced by USB, right? What you have on your computer is a USB connector. Well, that's also how we connected our microbit up, right? Is with a USB connector. So if what we do is we use the serial port on our microbit's, main computer to talk to the interface microcomputer, and then the interface microcomputer speaks USB to and from your host computer. So if we want to use this in sort of the normal way with a host computer, what we do is we go ahead and write a program that does this stuff, and then we use a terminal program. I got a comment that USB RS-232 is working from a Raspberry Pi, and I'm glad that it is. That's fantastic. And yeah, it should work. Should be all right. Right. So let's take a look at what we're doing here. I think I'm going to kind of skip to the end on this one. I don't know that the intermediate examples we really need to cover in super detail. Maybe. What is this naive censoring example, though? Not quite sure what's naive about it. See what the difference is, right? Oh, I see. Here it's just writing a byte at a time for some reason. It's weird that they needed a pointer there. Here it's writing the whole thing using a write macro, right? And the write macro here handles taking this stuff apart. Write is a Rust macro like println, except it takes a device that implements the write trait as a first argument. And so that way I can just write to the serial port. So this is all pretty simple. If I want to send something over the serial port, I get the serial port and I set it up. And here I tell it that, I want to use this peripheral as my UART. And don't worry about parity. Baud rate is just the bit time. In this case, about 100,000 bits per second. And these rates are weird because of history, because of convention. Don't worry about it. And we make a new UART port out of that. And here we're using the fact that the last thing in a Rust block is the value of that block. So the serial port is this thing. We locally make this serial thing, UART thing, and then we go ahead and get the UART port set up like that, and then we return it. And that serial thing, we write it out. That's the whole story. So the question is, how do I read that thing? And on Unix and Mac, on Linux and Mac, here's the deal, is that when this board is turned on, which I will do now, this right here is a device on my host computer. Oh, the E is for event or something like that. It's a fancy UART. There's an old UART that isn't E, and then there's the UART that has support for fancy interrupts and stuff. It's a dumb name. We can actually look, it's always worth looking, so let's just do it. It's always worth looking at the microcontroller manual, and we can actually look at the description of the UART. There we go. One moment, please. If we go to the microcontroller manual table of contents up here somewhere, should be the list of peripherals, and down here in the use because they're in alphabetical order, which of course is the best order. There's the easy DMA one and the not easy DMA one. That's what it was. And the easy DMA here just means that we can do something called direct memory access that we will not discuss here. I'm still writing that chapter in the Rust book, discovery book, that lets you lets the serial port send characters while you do something else. But that's the only difference. Is this is the newer peripheral. This is an older peripheral that's in there just for back compatibility with older boards. That microprocessor manufacturers do that a lot. They leave the old peripheral in there in case you have software already written that uses the old peripheral for a previous chip, so that you can keep using that software with the new chip. But this is the one with easy DMA. Here's a bunch of configuration. Here's transmission. Again, it shows what the waveform looks like I was drawing. Reception is the same way. And you can read this whole thing and understand at a very low level of detail how the UART works. And no, life's too short for that. We're just going to use the interface provided by the HAL through the board support package and through the BSP, and we're not going to try to make any sense out of all that mess. That sounds like a bad day. So anyway, I have this serial port on my host computer, and if I use a serial tool like Minicom, except the baud rate's being set wrong. This says 8 bits per byte, which is, believe it or not, a thing. And here's the bit time. What did we say? 115, 200, I think, or maybe something else. I don't remember. No. What baud rate did we set? These have to match. Yeah, it was 115, 200. All right. So if I start this up, the serial ports, my little terminal program is listening for something to happen on the serial port. And for some reason, it's decided that it would go in dark mode, which, thanks, Minicom, it never used to do that. And now if I go over here and actually, sorry. So now I need to go on a different terminal and actually run my program, which I will do right here somewhere. Cargo run release example send string. What we should see is when this program runs, it should send our string out the serial port, and we should see it. Yep, there we go. So when we ran the program, it sent that string out the
Hello,
serial
Professor
port.
Raj. Hello, Professor Brad. Your camera is too far away from the board. Please, I don't know if you can adjust.
Oh, there's nothing to see on the board anyway, really. So I just wanted to show you that it had turned on. But you're right, I'll move it down. Sorry, that was from when I was drawing. Yeah, once I turned it on and ran it, nothing happens on the board except that the microprocessor on the serial port actually sends the microprocessor sends on the serial port these bytes, the bytes that correspond to the character codes for this message. And then those bytes are received by the interface microcontroller, and the interface microcontroller sends these same bytes over USB, and then our host computer gets them over USB, and the terminal program prints them on the screen. So if I reset the board by pushing the reset switch on the back, it will print the message again because it runs the program again. And every time I reset the board, it'll print this message. Exciting. Now, we don't have to do this. You could also hook the UART to external pins that are not the interface microcontroller. And if you hook the UART to external pins, you can use a normal, use it as a normal serial device and hook it like somebody did to a Raspberry Pi, or hook it to a, or maybe you're using USB. Anyway, the point is you don't need to use USB. You can use this to directly connect, for example, 2 microbits together. You hook the transmit wire on one to the receive wire on the other, and now you can talk between things using serial. It's very exciting. Let's try one more program real fast. Not quite sure. Oh, when I hit reset, it ProBars gets really confused when you reset the board, which is fair. All right, so let's look at the final thing in the chapter. And that final thing in the chapter is echoing bytes that you type. So now we should be able to type stuff, and the serial port will receive it, and then it will echo it back out. It will send back out what we typed, and we'll be able to see it again. The only magic in this code, I think, is, first of all, here's a case where we might panic, is if, that's interesting. We don't panic here. We should just panic here. That's all. Anyway, we might buffer overflow. We have too many bytes, and we're typing faster than it can send stuff out. That should never really happen, but it could, I guess. And here, if we get a carriage return, that's the byte that you type that is sent when I push the enter key on my keyboard. And you probably wanted to actually send both a line feed and a carriage return, apparently in the wrong order, but you send a carriage return character to bring the cursor back to the beginning of the line, and a line feed character to move to the next line. And I have no idea why I put them up. Oh, rev. What am I doing? This is weird, and I don't know why it's written this weird way. Oh, I see. Because we're putting the bytes out in... No, I have no idea why I did that. That's super insane. All right. We want to put the buffer in. Oh, I see. We're not printing until we get to the end of the line. My bad. So we're accepting at most a 30-character line, I believe was how big we set that to. 32 bytes. We're accepting at most a 32-bit line, and while we're reading characters, we just push them into the buffer, which is just a vector, just an array, growable array. And when we get the carriage return, we decide to write out all the bytes in the reverse of the order received them, because we're pushing them onto the end, and now we want to pop them back off. And then we write a carriage return and a line feed on the end. And this code should be cleaned up. It's a giant mess, and there's no reason for it to be this weird. But anyway, the net result of that is that we should be able to run this. And again, I guess there's no reason to even show the board, because it's not doing anything interesting. It's just sitting there being a microcontroller board. There's no interesting behavior there. So let's now see if it echoes stuff. A, B, oops, it doesn't. Okay, well, that's interesting. Oh, no, right, A, B, C, D, and then I hit return, and it echoes it in the order reverse of the order I typed it. Interesting. All right. A, B, C, D, E, F, G, H, I, and there it is in the reverse of the order I typed it. And now if I type 32 characters, I'll just hold down repeat. Eventually it gets to 32 characters and it says, nah, your buffer's full. And if I hit return right now, I get however many A's it buffered up before the buffer filled up. So that's the serial port. We're having big fun with it. Control A, Q, I believe. Whoops. Control A, Q. Yes, leave without reset. And now we're done with the serial program. What is here? Oh, this. Never mind. There. All right. And that is serial. And we were supposed to stop 5 minutes ago for a quick break, so I will do it right now. Serial is cool. It's an old protocol. In the 1970s, when I started doing embedded stuff, I actually did serial back then. It was a standard called RS-232, where 0 was 12 volts and 1 was minus 12 volts, which is weirder than weird. We left that world a long time ago. RS-232 also had a whole bunch of wires because it was designed to hook specifically to hook modems to terminals. There were no computers at the time it was designed. And so it was a very strange protocol. But the basics of it are still the same in 2025 as they were in 1970. And that's kind of cool. We don't have very many things like that in computing. So let's take 5 minutes, and at 57, we will start again, and we will talk about a fancy kind of serial called I2C that's used mostly for the microcontroller to communicate with other devices on a board. So let's do that in a minute. Still have plenty of coffee. Things are going fine. Okay. Okay, here we are again. So the next thing I want to talk about is what's called I2C, which is the inter-IC communication protocol. We're all the way up to chapter 12 in the Rust Embedded Discovery book right now, which means we're skipping a lot of stuff. And one of the things I wanted to point out is, I'm trying to give you the whirlwind tour of Rust Embedded. Definitely go read all those other chapters and work through them on your own time, because there's a lot of good stuff there. I'm just assuming that stuff doesn't take as much explanation as the stuff I'm doing in the class. So please investigate. Please do jump on the Rust Edu Zulip, and let Mordecai know if you have trouble with the Rust Edu Zulip. I've had somebody report that they're having a hard time getting on. But get on the Rust Edu Zulip in our Rust Africa embedded channel and do the thing, I think, of talking to me anytime you have a question or want to poke at something or just show me something cool. That'd be awesome. So UART serial, RS-232 style serial is a point-to-point protocol. That is one end, you have two endpoints and they're connected to each other with two wires. One to transmit, the other one for the other one to transmit. And that's great. Sometimes it's simple. Asynchronous serial over those wires makes sense a lot of times. You can make it go reasonably fast, but not scary fast, because the UART itself has trouble when the bits are too close together deciding when to look for changes in the bit pattern. But unlike what the discovery book says, and I need to fix that, it's pretty routine these days to go at 1 million bits per second. And that's enough to do a lot of things. But the big problem is it's point to point. If I want to connect 3 devices to my microcontroller, I need 3 UARTs. And I almost never have 3 UARTs in my microcontroller. And if they all want to talk to each other, then things get really weird really fast. So what we really want is a serial bus protocol, and that's what I2C, the inter-IC communications protocol, actually is. The inter-IC communications protocol is a synchronous protocol. It does something a little different. It has a data line on which you can send zeros and ones. It also has a clock line, and the clock line's purpose is to say when a bit should be measured, right? And so with a data line and a clock line, you can do a lot of things. It's still a 2-wire protocol. And what happens is this data line is shared between all the things connected to it. So if you want to connect a bunch of things to your microcontroller, you just put them all on this bus, and when somebody wants to send stuff, they send it on this wire, and everybody else can see it go by potentially on that wire. And this clock line just makes sure that everybody's synchronized, everybody's on the same page. And so this can be faster because the clocking can make it faster, but the big importance of it is that it's a shared bus protocol. Now, normally when you're sending something you're sending it to one thing. When something's sending to you, it's sending to you. And so you probably want some kind of addresses, some kind of identifier that says which of these you're talking to. And I2C provides that. The controller and target devices are different. A controller is the thing that actually gets to decide who's sending. Essentially, the targets can only send in response to a controller request to send. So the controller says, hey, ADC, send me a measurement. And the ADC says, okay, and can send a measurement on the bus. During the time the ADC is talking to the controller, these people are supposed to shut up. The DAC and this other microcontroller connected on this bus are supposed to stay out of the way. The correct modern term for this is controller target protocol. Unfortunately, and super sadly, a whole bunch of older documentation, including the microcontroller manual and stuff, call this master slave. I didn't choose that name. CAN bus is very similar. That's a great question. CAN is a different kind of bus electrically, but it's the same idea. It's absolutely the exact same idea. There are a bunch of devices connected to the bus. There's addresses, etc. CAN bus is really mostly electrically different. Another one is another kind of bus that we should, or bus-y thing that we should talk about is SPI, the serial peripheral interface, but we're not going to because we just don't have time. But I2C is used a lot, including onboard. And it's possible to do 400,000 bits per second with the microbit. With other devices, you can go faster than that. So if the controller wants to send the target to a target, it says, I'm going to be sending now. Here's the address, the target address. This is a 7-bit address. And the 8th bit is used to say, I'm going to write. So it says, I'm going to write to the ADC, let's say. And so it picks the address of the ADC. How does it know that address? We'll talk about that in a minute. It sends start. It sends the 7-bit address of the ADC. The 8th bit is set to 1 to say, we're going to write. The target says ACK. It sends a message back saying, yeah, I'm ready. Actually, not the ADC, it'd be the DAC in this case, because it makes sense to write to the DAC. So the DAC says, yeah, I'm ready. And the microcontroller sends a byte, and the target says, yeah, I got that byte. You can do that as fast as you can. And the controller eventually says either stop or restart, and that's the whole story. The normal address length on I2C is 7 bits. There's also a 10-bit mode in I2C. Doesn't matter. Some newer devices use the 10-bit mode. For a read, it's the same way. The controller still runs it all. It says, start, and then, this address, and then this thing sends a byte back, and so, yeah. Now, remember I said this is often used to communicate with other chips on your board? That's the case for the microbit. The microbit has an interesting piece of hardware here, which is the accelerometer magnetometer, the LSM303. Let's go find that. Motion sensor, it says. I believe that's the motion sensor. It's a weird name for it, but yes, it's called that because on the older microbit V1, it was just a simple motion sensor. Here's our thing. This thing can detect, this is a chip that's sitting on the board. If we flip, let's go to the dot cam for a second and flip the board over and turn it off so the lights don't blind us. And you'll see a little line that says accelerometer, and it points at a little chip that you can barely see down here in the left-hand corner. If I get it down here, it's like it says, it's an accelerometer. Let me turn on the light. Ooh, that's blinding. It's terrible. And then we'll hit the autofocus and see if we can autofocus it. There we go. So that little teeny chip down there in the corner of the board has a magnetic compass in it. That's what we call a 3D compass. It can tell not just which direction you're pointing, compass direction you're pointing, but whether you're pointing up or down. There's an accelerometer in there, which measures acceleration, measures force placed on the board that moves it in the X, Y, and Z directions. So that one little chip is all of that, which is pretty cool. Look how tiny it is. It's like 100th the size of the speaker, which is hilarious. And that chip is what we're going to talk to with I squared C, because if we look at the schematic, you'll see that the way this is hooked up is I squared C clock and data are connected to these pins right here on the chip. And if we go back to the microcontroller, we'll see that it's also hooked up. By the way, this is being used as a bus. Not only are these hooked up to this bus, but the interface chip is hooked up to this bus. And so this bus is used both for our microbits microcontroller to talk to the accelerometer magnetometer, but also used for it to talk to the interface chip. And that, by the way, is super annoying in a way that I'll describe someday later. But that's what's going on there. And so if we want to talk to this chip, we need to know what this chip's deal is. And to do that, what we always do in this situation is we go get the data sheet of the chip. And in this case, we have it linked here. And the data sheet, these little off-board parts, just like the microcontroller has a manual, every chip on the board pretty much has a manual as well. In this case, the manual is the manual for the LSM 303 AGR, accelerometer and magnetometer. I don't remember what AGR stands for here. Gauss meter and rotator, I don't know. So here's an overview of the thing. And here's a bunch of stuff for the electrical part. Here's some stuff about what acceleration and magnetometer really are. Here's some description of the functionality. And here's the I squared C serial interface all the way down at page 37. And so if we look at this, and again, I'm sorry, it's all master slave. If we look at this, it says, there's two devices connected to this I squared C bus. So not only is this chip connected to the I squared C bus, there's effectively two separate devices inside the chip connected to, inside that package connected to the I squared C bus. There's an accelerometer, which has this 7-bit address, and there's the magnetometer, which has this 7-bit address. And so that answers the question of how do you know what address to use? You use the address with the chip. Now you might wonder, what if I try to connect two accelerometer magnetometers to the thing? Well, that's not going to work very well because they both share the same address. There are sometimes ways to change the default address. Yeah, this is the default address. So you can actually change the address of one of them. And the way you would normally do that is you'd turn one of them on, change its address, then turn the other one on. And that would all be wacky hardware that you would not normally have, because normally you wouldn't want more than one of these connected to the same I squared C bus anyway. And so there's this notion of registers. Almost all I squared C devices have this notion of having internal registers, which each have their own sort of register address. And you can read and write those registers to say what the magnetometer or accelerometer is doing and what it should be doing. And so a normal write to the accelerometer writes the register address of the register you want to mess with, and then writes the data that goes in that register. And similarly, a read, there's SPI, we don't care. I don't know what happened to I squared C here. Here's I squared, this is SPI, I don't care. sorry, I got lost here. So yeah, you give a register and you give a data to write, or you give a register to read, and it will send back the contents of that register is the point. And so if you wade through all this, you can figure out all the things. Here's all the registers that are notionally on this device. There's a status register. The register we'll mess with first is the who am I register. You basically ask for register this register 0F or 0001111, and that gives you back this value every time. It's just a guaranteed return. And you do that to check to make sure you're talking to the right device. So let's look at some code finally. I remember code. That was a thing. And here's us using a really low-level interface to talk I²C directly to the device. And what we're going to do is we're going to ask both the accelerometer and magnetometer. We're going to write the who am I message to them. And we're going to access the who am I register on the accelerometer and the who am I register on the magnetometer, and we'll get back the response from that. So that's all we're going to do. And again, I won't show you the board because nothing interesting happens on the board. What was this example called? It was called chip ID. It really should be probably called who am I. Is it turned on? Maybe not. I don't remember. Yeah, not. Okay, there we go. Let's turn the board on and try again. Hey, and there it is. So we've actually successfully written bytes onto the I²C bus and read back the contents of some registers on the accelerometer and on the magnetometer that are attached to the bus. Let's look at that in a little more detail. Nope, wrong. So again, this is the bus I²C bus addresses of the two chips. Notice that we can write nice binary numbers in Rust with 0B. Here's the registers that you're supposed to use for who am I for the accelerometer and the magnetometer. And so what we're going to do is just get a new interface. The I² C interface on the microbits processor is called the TWIM for two-wire interface master. And so we make a new one of those, and we make sure to use the I²C internal chips on the board and a TWIM controller. And we're going to use the 100 kilohertz frequency because that's the 100,000 bits per second frequency, because that's the frequency that the chip talks. Here's a little array with nothing in it that we're going to use to sort of put messages in. So we'll get the results into. So we go ahead and say, oh yeah, send this register thing to the accelerometer, and then read back the result into this array here, which happens to be just a 1-byte array that gives the thing. We'll do the same thing for the magnetometer, and then we'll just show what we got back. Notice that these unwrap. It will panic if talking to the chip fails, but it did not panic, so it did not fail. So that's the low-level interface, and you can absolutely sit there with the manual for the LSM303 and figure out what all the registers do and sit there and talk to that device using that. And that would be a long few days of figuring out an interface. Fortunately, this is Rust, and we have crates.io. And in particular, on crates.io, we have the LSM303 AGR crate. So this is the single register stuff we already did. And The LSM303 AGR crate is just a Rust library that absolutely is just a library that uses talks to the chip through I2C or SPI, and we're using I2C. So here's an example of using this chip. Let's get the documentation here, docs/blah, and this is the crate. And it basically, instead of having this low-level interface where we have to read and write the device that registers directly, it does all that for you and gives you some sane people interface to measure acceleration and compass values. So all the work's effectively been done for us by some saint who decided to publish a library for this. So if you look at examples/slow Excel, what we do here is we use the LSM303 AGR crate. We get the acceleration mode, output data rate, and LSM303 AGR structs. And we go ahead and get our I2C port set up again. This crate also needs a timer because reasons, so we build one of those. And then we make a new LSM303 AGR struct, right, using the I2C interface that we just built. And now it will talk to I2C for us from here on out. We don't have to think about I2C anymore. We initialize the sensor. We set the acceleration mode and output data rate. So we say, I want high resolution at 50 samples per second. We give it this timer to use. We lend it this timer to use so that it can do the timing. And then we just sit there, and if there's new data, which is a thing provided by the interface, then we get that data and we show the acceleration in milligauss. No, millig's, I think. I don't remember. That, I guess I can look at the documentation. Acceleration. Get measured acceleration. Result is an acceleration struct. Millig's. So to understand how the accelerometer works, you have to understand a little physics here, because this is how embedded goes sometimes, is that it isn't just computers and electronics, it's actually a domain. 1g is the acceleration induced on an object when you drop it, right? 1g is essentially one force of gravity's worth of acceleration. So if I pick an arbitrary object and I pick it up here, if I let this go, this starts falling downward with an acceleration of 1g, which is a pretty good solid acceleration, one force of gravity. And so that's how much acceleration is a Gauss, or sorry, is a G. And then we're going to get our readings in millig's. So that was the 1,000 millig's of acceleration. And so let's actually run this example. On our board. And here I'm probably just going to want to, yeah, I don't know what I'm going to want to do. Anyway. And you'll notice that in the X and Y direction, I don't have very much acceleration. But in the Z direction, I have almost a G of acceleration. That's because gravity is pulling down on the board. Now, the board, if you look at it, is just sitting there not doing anything. It isn't like I'm moving it. It's that gravity is accelerating it downward, but the table is pushing back up, right? My little coaster there is pushing back up on it. So if I, sorry, one moment, please. If I wiggle it back and forth, if I grab it and do this, you'll notice that it also now gets an acceleration in the x direction. And if I wiggle it this way, I get accelerations in the y direction. I'm not very good at this, so it's not that well resolved. But so apparently the positive x direction is, if I remember right, this way. The positive y direction is this way, I think. Maybe the other way around. And the z direction is out of the board, right? So that's why it's into the board. So it's so we have a 3D accelerometer. We can measure the positions that things. We can measure the acceleration that the board's experiencing. Now, if you're a physics geek, you know that the integral of acceleration is velocity, and the integral of velocity is position. So in principle, if we can keep measuring the acceleration very accurately as the board moves around in space, we can also measure its position in space. There's some problems with that. One is that gravity messes you up when things are sitting in position, but the other one is just that those integrals accumulate a lot of error very fast. That's not a very reliable way to measure the position of the board in space. But for stuff like measuring whether the board's being wiggled, it works very well indeed. And for figuring out when the board's sitting still, which way it's oriented, right, it works really well. As I move the board, as I tilt the board this way, right, now the acceleration is in the negative y direction. And if I were to hold the board this way, the acceleration's in the positive x direction. So yeah, now I can tell how the board's oriented when it's sitting still by how gravity is pulling on it. And that can be really handy. We'll put it back so that it's flat. But the important things here are, one, that the accelerometer is a pretty cool toy, but also two, that with I²C and a device crate, it's very, very simple to talk to this thing and actually get those measurements. So let's look at the main example of the chapter, and then we'll be out of time. What does this do? This one is going to be a compass and accelerometer. And so this is basically the same thing, but it responds to commands by reading back either the through the serial port by measuring acceleration or measuring magnetic field. So now we're going to combine a whole bunch of stuff again from all the chapters we had. We'll go ahead and run this app, but before we do that, we'll go start Minicom again. Let's go Minicom. All right, so now we're talking to this board with Minicom here so that we can eventually do stuff with it. I don't know why it went white all of a sudden, but there we are. Super weird. I don't understand this thing at all. Anyway, let's run this. And it says it's set up. And now if I say mag, it reports magnetometer reading. And if I say ACC, it reports the accelerometer reading. So we're talking to the chip, to the microcontroller, to our microbit, through the serial port via USB. And then it is talking in turn to the accelerometer magnetometer via the I²C bus, and it's getting its reports back. So we have an accelerometer that says we're mostly pointed down, although we're at a bit of an angle. And if you look at the actual board, you can verify that we're at a bit of an angle. There's actually a little bit of a tilt here. And if I flatten it out completely, probably then the next time I ask for the accelerometer command, it says, yeah, that's about right. It's about flat. And then if I ask for the magnetometer position again, I get an interesting result, which is that the X and Y have some values, but also the Z has a very strong value. Why would the Z have a very strong value? Well, because I'm in Oregon, and Oregon is sitting on a weird magnetic anomaly. And actually, the magnetic field in Oregon points down into the ground really hard, which is strange, but there we have it. It absolutely does. And so compasses act weird out here. It's a thing. Your results in Africa are going to be different than my results in Oregon. The other thing that messes up the magnetometer, of course, is any metal that's floating around in the environment. The magnetometer will see that as something it's attracted to, just like you'd expect. And so metal messes stuff up, and we're real close to the monitor. But the main thing is gravity's magnetism's into the ground here. Let's turn the board and ask for another reading. I guess I can turn the board. Come on, board. Let's turn it around like this somehow. I guess like this is a good way. Now it's turned about 90 degrees from where it was. Let's ask it for a magnetometer reading again. And now you'll see that the X and Y are way different. The Z is not that different. The component that points to the ground is about the same. But so I can use this to determine direction a little bit. And that's handy. And the combination of the magnetometer and the accelerometer is even more handy. But this is all just straight library code talking to the I2C and serial bus. It couldn't be more simpler. So that's what I got for you today. Is that hopefully that was useful. And on Monday again, we will talk about another batch of stuff. In the meantime, please, if you're interested in talking with me, get on the Rust Edu Zulip and join the Rust Africa Embedded channel. I'm absolutely happy to chat with you there. Thank you. This has been big fun. I will talk to you again in a bit. Take care.
Okay. Thank you very much, everyone, for attending. Another point to iterate over is this course is from the Rust Discovery MV2 book, which you can always check out. And every code that's being used is being pushed to the GitHub, the official Embedded Rust Africa GitHub. And one thing for sure is join the Rust Edu Zulip channel, where you can interact more, ask further questions. We want to see what you are doing with the board too. We want to see how you are playing around with it and also get clarified. And Professor Brad is very, very open. You can always reach out to him to ask some of your questions, which will be answered. For now, stay tuned and we'll see you guys next week. Bye-bye.
Take care.